Okay, we're going to do a velocity analysis of a slip velocity. Okay, so we could call it slip velocity analysis. In this case, we're using figure P624, and in this particular figure, we are given a few knowns. So VA2 is equal to 20 inches per second. That's our known velocity. And we also have some known lengths. So these would have been either part of the design or determined using position analysis. And so L2, our crank length, is equal to 2.5 inches. O4A, from O4 up to this point A, is at this present time equal to 4.1 inches, but that's a changing amount, and we'll talk about that later. And we have O2 to O4, that length is 3.9 inches and it doesn't change. Theta 2, the angle of our crank, you see here it's a little bit below the horizontal, so we're going to call it 11.5 degrees, and there's a negative here, but generally just kind of think of angles as positive, but this one is below the horizontal, and so I'm calling it negative for this purpose. And theta 4 is equal to 56 degrees. We'll show that drawn in later. Theta trans is negative 61, and theta slip is 29. So both of those we will talk about as we proceed. And we're going to use analytical methods, and so we will be getting exact answers. And so you should expect to see some trig here to make sure that we're not just measuring things with a ruler, but we're getting answers that are perfect for omega 2, omega 3, omega 4, VA4, V slip, and V trans. So let's go ahead and get started. First thing we want to do is acknowledge our effective length 4, because in this particular case we have a changing length 4, and it goes from O4 up to A. And let's just indicate that, just so we remember, this is effective length 4, and is a changing length. The direction here, trying to get it horizontal here best I can. It's measured from the horizontal. That's our theta 4, and that was given to us as 56 degrees. And you may recall that I said that we had a theta 2 of about 11.5 degrees, a little bit below the horizontal there. Now we're going to draw in our axis of slip, and it's always parallel to the slot, drawing it here in green, and it is also given to us, since this part of that would be part of position analysis, and it is 29 degrees. And try to get the same horizontal, everything's measured from the horizontal, same value here, and that is a theta slip of 29 degrees. Theta 4 and theta 2, we've gotten our theta 2, our theta 4 is drawn in, and our theta slip. Going to go ahead and draw in our VA4. It starts at A and is always perpendicular to length 4. In this case, perpendicular to effective length 4. We've drawn it in here in red. Now, parallel to the axis of slip is VA42, which we're drawing in blue. And VA4 and VA42 always have their heads at the same spot based on our vector addition. VA2 plus VA42 equals VA4. So we drew our VA4 a little long, and so I'm putting the head of it back there because VA4 equals VA2 plus VA42. VA42 and V slip are the same. Now, if we were doing a graphical method, we would begin to, VA42 is parallel to our slip axis. We would start to measure things, but in this case, we're doing an analytical method, so we have to be very careful with our angles. So a right angle between VA2 and link 2, and a right angle between VA4 and link 4. And of course, when you have right angles are 90 degrees. Now we're going to draw in our V trans. V trans here, drawn in kind of brownish color. And there we go. It is always perpendicular to the slip axis. So give us another horizontal here. We really need to pay attention to this triangle because this is where all the interesting stuff is happening. So let's get some other angles here that we can measure. We're going to have a measurement for VA4 and VA42. Get some angles there. Okay, so we got a bunch of horizontals that we can measure things from now. So here's our angle. We're going to call this angle alpha, and those two angles are equal on either side. And that angle is our slip axis. Remember, VA42 is always parallel to the slip axis. So since our VA42 is parallel to our slip axis, and you can kind of see these little parallel lines that I have here just to show that the blue and the green are parallel, then our angle here, alpha, is going to be equal to our theta slip, and theta slip was given to us again, so that's 29 degrees. Now, our beta is here and here, measuring the angle for our VA4. How is our VA4 proceeding? Now, we know that VA4 is perpendicular to length 4. And length 4 has a theta 4 of 56 degrees. So VA4 has to be either theta 4 plus 90 or theta 4 minus 90. So which one do you think it is? Theta 4 minus 90, since it's coming down in that direction. And that means our beta is equal to 56 minus 90. The absolute value of that gives us 34 degrees. Now all the way over to VA2, that's an angle that we're going to label gamma. That should be, again, since this VA2 is perpendicular to length 2, it's either theta 2 plus 90 or theta 2 minus 90. And in this case, it's going down in that fashion, so it's theta 2 minus 90 or 101.5 degrees. That makes sense, right? Because that gamma is bigger than 90. And here we have a sigma. And the sigma is the last angle in that triangle. And so we have a triangle here. Black side, blue side, and red side. We know that this part of the triangle is going to be the gamma minus our beta. We know this side of the triangle, or this angle here, is a beta plus alpha. And this angle over here is our sigma. So sigma should be equal to 180 minus this angle and this angle. And so I have both the angles there. So we end up with a sigma that is equal to 49.5 degrees. So now we know all of the angles within that triangle. And we can proceed with sine law because we also know one of the sides, and the side that we know is VA2. So VA2 is equal to 20 inches per second, and VA2 is opposite of beta plus alpha. Opposite of sigma is VA4, so VA4 over sine sigma, or VA4 is equal to 17.07 inches per second, which means omega 4, which is VA4 divided by length 4, which is the length, the effective link length, O4A of 4.1. So we have 17.07 divided by 4.1, or 4.2 radians per second. And you may recall that since the block, link 3, is sliding inside of link 4, they must have the same angular velocity. Otherwise, that block would break out of the slot. And so omega 3 and omega 4 are equal. Again, VA2 being our known opposite of beta plus alpha. And VA42 is opposite of gamma minus beta. And so we can now solve for VA42. VA42 is going to be equal to V slip. VA42 and V slip are always the same. And once we solve that equation, we get our 20.7 inches per second for V842 or V slip. Omega 2. We must also solve for omega 2. VA2 was given to us this time, not omega 2, but VA2 is equal to omega 2 times L2, excuse me. So omega 2 can be found as VA2 divided by length 2. VA2 is given to us as 20 inches per second. Length 2 is given to us as 2.5 inches. And so our omega 2 is 8 radians per second, and that is clockwise. Last but not least, our V-trans. V-trans is drawn for us here in brown. And we notice that it's part of a right triangle. So it makes it a little bit easier to determine. We don't need sine law. We just say that V-trans then is equal to VA2 times the sine of gamma. Oh, I'm sorry, sine of sigma. So we get 15.2 inches per second for our V-trans. And that's the end. Thank you for watching.